Neural networks. They look formal, mathematical, respectable. Yet, underneath the calculus, they sit squarely at the intersection of science and charades. At its core, the process is one of mild disappointment. We watch the model make a prediction, notice how hilariously wrong it is, and gently shove it in a slightly better direction by changing its internal parameters up or down. That's it. No grand theory, no cosmic equations unlocking the universe. Just cute, but no. Try again. And yes, if you want the fancy version, we measure how the loss changes when each parameter moves an infinitesimal amount, run those sensitivities backwards through the network with backprop, and update the weights in the direction that hurts a little less. But even that is just a technical skin around one idea: course correction. I call it intelligent nudging, advising a mountain of matrices that desperately want to speak human. And somehow, after billions of these nudges, something that looks like intelligence crawls out the other side. Neural networks are basically structured guessing with math attached to help make guesses less stupid. The structured part is the gradient. Sounds mystical, but it's not. It's high school calculus, a derivative, a rate of change. All it tells you is, if I nudge this number a tiny bit, how much does the output shift? That's it, a direction, and how strongly that direction fixes the mistake. Big gradient? That parameter messed up. Shove it hard. Tiny gradient? Barely contributed. Poke it gently, like tapping a sleeping cat. Basically, a neural network learns by nudging billions of numbers toward less wrong. The gradient tells you how many steps to take and in which direction to move. It captures how steep the landscape is and how strongly the model should respond. Alpha, the learning rate, decides the size of each step we actually take. When alpha is too large, the model overshoots the target and keeps oscillating. It never settles into a stable solution. When alpha is too small, progress becomes painfully slow. Learning happens, but at a pace that's practically stalled. Effective training depends on keeping these two in balance: the signal from the gradient and the restraint imposed by the learning rate. Do this billions of times, and blind guessing turns into informed guessing and intelligence starts to emerge. Transformers didn't escape this, they just made it fancier. We quickly realized that word embeddings alone weren't enough for high accuracy. The model needed to understand where each word appears, not just what it is. So we add positional encoding, another carefully designed nudge. Each word embedding is adjusted based on its position in the sentence. Then, attention nudges those embeddings again, this time using relationships across the entire sentence. Each word updates its representation by absorbing contextual signals from surrounding words, becoming progressively more context-aware with every layer. If you want the deep version, we have a full video lifting that hood open. After billions of gradient steps, embeddings gain structure, attention captures relationships, predictions become coherent, and the system behaves as if it understands. But nothing magical happened, just derivatives, just gradients, just tiny nudges repeated endlessly. This isn't classical law-driven science. It's a science of refinement, a science of feedback, a science where intelligence isn't discovered, it's sculpted, one microscopic nudge at a time.